Okay, we are right on time. It's 12. We'll go ahead and get started. Thank you everyone for attending Power America's technical webinar for this month. Today we have Dr. Arash Salami with us. So Dr. Arash, he's the Senior Manager of Technical Marketing and Silicon Carbide Technology at Navitas Semiconductor. Dr. Salami's previous experience includes senior technical marketing and silicon carbide device design roles at onsemi and also at Alpha and Omega Semiconductor. He received his PhD from KTH Royal Institute of Technology, and where he developed a wide range of 4.5 to 15 kV silicon carbide BJTs and PIN diodes. As you can see on the screen, this is the topic that he's going to be presenting to us today, this afternoon. The presentation is going to be for 50 minutes, and we will have a 10 minutes Q&A session towards the end. As Dr. Salami is presenting, please feel free to type your questions in the Q&A box, and we will attend to that towards the end. So Arash, you can take it over.
Thank you very much for your kind introduction and also inviting me to participate in this webinar. And hello, everyone. It's my pleasure to be here to present our latest results on 3.3 kilovolt and 2.3 kilovolt range-assisted planar silicon carbide MOSFETs and high reliability silicon carbide power modules for energy infrastructure applications. Here's the agenda of my talk. First of all, I have a short overview of Navitas. Then I'm talking about the grid, energy infrastructure, and data center applications. Then I'll cover the technology, the unique technology that we are using in Navitas named Trench-Assisted Planar. After that, I'm covering the ultra-high voltage silicon carbide technology, including 3.3 and 2.3 kilovolts. And then I'm covering the epoxy resin potting power module technology, which is the technology that we developed in Navitas. I'm talking about the future technologies, and then I'll summarize my talk. Let's have an overview of Navitas. Navitas was founded in 2014 on gallium nitride development. Since then, we are integrating a gate driver for ultra-fast switching, integrated protection for robust and reliable performance, and most efficient and safest GaN power IC products. We have multiple GaN technologies, including GaN Fast, GaN Safe, GaN Sense, and GaN Safe. We recently reported the bidirectional GaN switch with substrate clamp, and so far we have shipped more than 250 million gallium nitride power devices with excellent field reliability. In 2022, Navitas acquired GeneSiC, which was founded in 2004. So in GeneSiC, we have a 21 years of silicon carbide development history. GeneSiC established the world's only trench-assisted planar technology that I'm covering in the next slides. We have unique multi-point shielding design for superior reliability, industry-recognized leader in critical performance figure of merit, simplified, cost-efficient manufacturability. We are commercially silicon carbide power devices rated from 650 volt to 3300 volts or 3.3 kilovolts devices. But in the R&D part, we have developed up to 20 kilovolts, leading supplier of high voltage silicon carbide. And so far, we have shipped more than 22 million power devices with excellent field and reliability. But since this webinar is related to the silicon carbide, let's have a look at silicon carbide portfolio that we have in Navitas. Here is the system power from 10 kilowatt, 100 kilowatt, and more than 1 megawatt with different applications like solars, electric vehicle chargers, data centers, and then we have the grid infrastructures. And for all these applications, we have a device from low voltage 650 volt to 3.3 kilovolts on different packages on the discrete devices, backside and topside cooling. And also we have modules with a unique technology named epoxy resin technology for 1200 volts. And recently we developed for 2.3 and 3.3 kilovolts with this technology. Also, we have the bare dies with KGD or non-good die with EV traction, 750 to 1200 volts. And for high voltage and ultra high voltages, we have the bare dies from 1700 volts to 10 kilovolts. Now let's talk about the grid, energy infrastructure, and data center applications, which is a hot topic these days. But the first question for this topic is how much power we need. And this is the case that we need to discuss about the power demand. This slide shows that the number of the data centers deployed globally has doubled in last decade to 7,000. Just look at this part, doubled in a decade. Now, if you go back to 2022, we globally consumed the energy for 60 terawatt hour. And now, by 1 year later, in 2026, we need to increase it to 1,000 terawatt hour, which is more than double of the energy that we consumed in 2022. In order to look at this number and have an idea how much this power we need, this is the level that US is likely to reach on its own by 2030. So we need this energy by 2030 in the US. However, we need this energy or power globally by next year, which is a very high demand. This is not only the US. For example, Sweden data center usage is expected to double by 2030 and double again by 2040. And the same situation for other countries. For example, in UK, with a 5-fold growth predicted within the next decade. And now, if you look at the 2030, by 2030, which is 5 years from now, the power is expected that the globally consumed by 88% of the global electricity usage, which is not the usage for example, streaming the video on Netflix or Amazon. And this is only one reason. We are increasing the demand of AI. This is the only reason. And by this, we can say that we are building the future of AI, which demands a massive energy infrastructure. Now let's see why we need this demand of AI. This slide shows an overview of the significant data center transformation. If you look at the top side here, we have the traditional 12-volt data centers. When we are stepping down the voltage from 13.8 kilovolt AC to 220 volt AC three-phase, utilizing a bulky and heavily transformer 50 hertz. And then we are stepping down this voltage to 12 volts using a converter of AC-DC. And finally, by using a DC-DC converter, we are powering the components like CPUs and GPUs. The power density of this server rack is 10 to 20 kilowatt, and the components are using 100 to 300 watts. The total energy efficiency of this architecture is only 70 to 80%, and the reason is this architecture based on only silicon power devices. Even with limited gallium nitride or silicon carbide usage that we have today, we have a low efficiency. Now let's look at today's AI 48-volt data centers. The first stage is the same as the traditional one. We are stepping down to 220 volt AC. But here in the server rack, we are stepping down this voltage to 48 volts. If you compare the voltage 48 to 12 volt, it means that we are increasing the voltage. In other words, we are reducing the current flow, which results a lower power loss. Sorry, it seems that we have an alarm here. It's just a test, so just a moment. Hopefully, it will be finished soon. Is it 2 minutes? So sorry, I'm just.
Is it the fire alarm, Arash? Okay, we'll just give him about 2 minutes.
In the meantime, this is Victor. I wanted to say hello to everybody. We have a very good participation in this talk. Very interesting stuff on the data centers, which are very timely, and we're looking forward to Arash coming back and continue his presentation. Thanks for being here.
Sorry, everyone. It was supposed to have this test, fire test, 2 hours later. I don't know why they tested now. Can you hear me now?
Yes.
Yes, we can hear you, Arash. Please
can
proceed.
Lavinia, can you hear me?
Yes. Yes, please continue.
All right. Again, sorry, everybody. It was supposed to be actually done 2 hours later. I don't know why they did it now. By the way, I was talking that in the second stage, we are stepping down this voltage to 48 volts, and by increasing this voltage from 12 volts, obviously we are lowering the current flow, and we are reducing the power loss. And then we are converting DC-DC and powering the components with power more than 1,000 watts. The power density of this server rack is more than 100 kilowatt. And in this architecture, we are using 650 volt gallium nitride and silicon carbide in the AC-DC converter, 100 GaN in the BBU battery backup, and also 100 GaN in the DC-DC converter. Thanks to significant usage of gallium nitride and silicon carbide, now we can increase the total energy efficiency from 70 to 80 to 90%. And the market requirements by 2030 is 1.4 billion per year. Now let's talk about the future. In future, we have the future AI 800 volt data centers. As you can see, we are replacing this bulky transformer 50 hertz with solid state transformer AC-DC converter. So we are stepping down this AC voltage, high voltages to 800 volt DC, utilizing ultra high voltage silicon carbide 2.2 and 6.5 kilovolts. And then we're using a BBU with utilizing 1200 volts here. And then in the server rack, we are stepping down again to 48 volts. DC-DC converter instead of AC-DC converter with 650 volt and 1200 volt silicon carbide and 650 volt and 100 volt gallium nitride. And then again, by DC-DC converter using 100 GaN, we are powering the components, CPUs and GPUs with 3,000 watts, 3 times higher than the previous one that we are using today. By this architecture, we are able to increase the total energy efficiency more than 90% by accelerating the gallium nitride and silicon carbide usage. And the marketing requirements by 2030 is $2.6 billion per year. So obviously, AI is rapidly reshaping the data center landscape. And also, AI 800-volt data centers and SSD adoption obviously require gallium nitride and silicon carbide components. The good news is Navitas can support the data center grid to GPU with different range of voltages and devices, both gallium nitride and silicon carbide. As an example, we have the 100, 200 gallium nitride, and also 650 volt bidirectional gallium nitride. And also we have 650 volt silicon carbide up to 10 kilovolt and even higher for the silicon carbide. And by this, we can support the different parts of the grid, the data center grid to GPU in SSD, in UPS, PBU, air conditioning and power chill, and server power. Now let's look at this slide. This slide shows that high voltage DC is critical for future AI data centers. But why? Today's data center uses 54 volt in rack power distribution, which is limited to a few hundred kilowatt rack. It means that the power transfer is doing by the copper wires. And by this voltage, we need a high current in order to transfer. And bulky copper bus bars requires for this transferring, and obviously we have high power loss. Now, AI requires significantly higher power to process. And it means that we need higher power. So if we have a constant voltage, we need higher current. And again, we have higher power loss. So in other words, we need to increase the voltage instead of increasing the current. And this is the reason that the new architecture is required plus minus 400 volts to 800 volt DC. As a comparison, here you can see we need a cable to transport 200 kilowatt of current. This is for 48 volt DC. And if we increase the voltage to 400 volt DC instead of 48 volt, obviously we need lower cables, coppers. So it means that we have lower power loss, the first item. And the second one, we have lighter and lower cost. And finally, 800 volt DC directly powers the IT racks. It means that the copper wires can be reduced by up to 45%, as I explained here. End-to-end power efficiency improved by up to 5%, and maintenance costs reduced by 70%. And the reason is we have fewer PSU failures. Now look at the energy and grid modernization. Actually, AI data centers are becoming the intelligent layer that modernize the grid infrastructures for different components, like electric vehicle charging systems, renewable energies like solars, and also battery energy storage systems, or BESS. Obviously, all these components need a high efficient, high power converter in order to connect with the three-phase grid, 34.5 kilovolt or 13.8 kilovolt. And this is where SSD comes in. Actually, SSD is a leap technology that we need. Here is the typical solid-state transformer, or SSD, based on input series, output parallel ISOP modular design approach. Now the question is why this approach is important, because this ISOP enables stable power and voltage. In other words, we can easily adjust the voltage and power by removing or adding the modules. And what are the core of these modules? Silicon carbide devices. High voltage silicon carbide devices like 3.3 kilovolt and 2.3 kilovolt discrete and power module solutions enable simpler design of power converter stacks, which results in a higher efficiency, smaller footprint, and increased reliability. So now we reach to the point that we need a technology for silicon carbide, which provides us a high reliability, high performance, and also more robust. And this is the technology that we are using in Navitas and before that in Genesee, which named trench-assisted planar technology. For explaining this technology, let me start with the traditional planar technology first. Here is the traditional planar vertical device for powered silicon carbide devices, where we have the source N plus here, and then we have the gate over the JFET, and then we have the drift layer, and finally we have the substrate and drain. By applying in voltage on gate, we are making a channel over the P-well here, and by applying the VDS, we can have the trace of electrons from source to channels to the JFET CSL, and then we have kind of spreading in the drift layer, and these electrons are collecting in the drain. But there is one challenge between silicon carbide and silicon, or if let's compare the silicon and silicon carbide. Actually, the electron mobility in silicon carbide is lower than silicon, which obviously will increase the RNSP or specific on resistance. In order to reduce this parameter or RNSP, there are different ways. One way is reducing the cell pitch, so we can shrink the device. And another way is reducing the gate oxide here in order to improve the channel mobility and improve the RNSP. However, when we reduce this gate oxide, actually we are making a huge electric field on the oxide, which will cause some reliability issues, and even at higher electric field, it causes breakdown. In order to protect this gate oxide in this traditional planar, normally we are putting a shield. These shields are these P+ implantations under the P-well that can protect the gate oxide by making a good shielding here. Another way, as I mentioned, is reducing the cell pitch. And the third one is normally in silicon carbide, the electron mobility is not symmetrical, where we have a higher electron mobility in C axis, which is the vertical part, compared to the XY plane as we have here at the surface of the silicon carbide. And this is the reason that we went to trench devices like this. First of all, we can have a smaller cell pitch. Secondly, we can have a shorter channel by implantation here. And finally, the channel mobility or electron mobility in the vertical parts or the side walls are higher than the horizontal part. But again, we need to protect the gate oxide here. And for this, we need to have the P+ implantation under the gate oxide. But now suppose that any misaligning in the process, it makes some reliability issues. For example, if we have a misaligning to the left, then the right part will be unprotected, and we have a high electric field on the right side, and it will cause damages or low reliability and even breakdown of the gate oxide. There are other techniques to overcome this, which is one of them is double trench. In the double trench, if you look at the middle part here, it's exactly the same as this traditional trench. We have the N+ source, P-well here, we have both channels, and then we have the gate. But instead of having the ion implantation under the gate, normally we can make two dummy trenches here, and then having this P+ implantation under these dummies. And by this P+ implantation, then we can actually provide a shielding under the gate oxide. This is one way. And another way is asymmetric trench. In this asymmetric trench, normally we can sacrifice one side of the cell here on the right-hand side by P plus implantation in order to protect the other side, which is the left-hand side. So if you look at this asymmetric trend, normally this part is active, we have the channel, and the right-hand side is not active. It's just for protecting the left-hand side. For this design, normally we are making this side walls, or it's better to say the better view is having the side walls in A phase, which has the higher channel mobility. However, all these trenched devices, first of all, they have more complexity. And secondly, we need more steps in order to make them, which will increase the cost. And finally, any misaligning here results in high electric field under the gate oxide or even at the corner of the gate oxides will reduce the reliability. And this is the point that we consider all of them traditional plane and the trench devices and combine all the advantages to make a new technology named trench-assisted planar technology, which is here. So as I mentioned, the gate planars are more robust compared to the electric field protection. So the trench-assisted planar is a gate planar. So we have the channels at the surface, N plus, P well, and then we have the channel and drift, substrate and drain. But we have also a very shallow trench on the source area here. And in this shallow trench area, after that, we can have the P plus implantations. And by this, we are making other steps or extra steps of the P plus implantations. What is the reason of this? By these extra steps or multi-steps P plus implantations, we have a better protection of the gate oxide here. So obviously the gate oxide here sees a lower electric field compared to the traditional planar. But this is not the only advantage. The other thing is, as I mentioned in the previous slide, one way to reduce the RNSP is shrinking the cell pitch or reducing the cell pitch. Here is the traditional planar devices when we have the gate oxide here and another gate here. So we have one cell here and another cell here. And between these two cells, we have the source. What happens if we reduce this source area or gap? Actually, we need a good metallization here for the source contact. And for having a suitable metallization, we need enough surface in order to make this metallization. And it makes a limitation for shrinking or reducing this source pad area, the source area gap. But by our technology, with having this shallow trench, we are making suitable or enough surface in order to have a good metallization. And by this, we can reduce the source gap and reduce the cell pitch. And this is another reason that we can reduce the RNSP. All right. Another advantage is, thanks to having these multi-steps of P plus implantations, we are making a better current spreading compared to other planars, and obviously better than trenches. If you look at here, the current can easily spread over these steps and have a better current spreading compared to the traditional planar, as I mentioned. And this is one huge benefit, especially for high temperatures. And this is one reason that we have a lower RDS(on) at higher temperature compared to other designs. Now let's compare the traditional planar and the standard trench here regarding to manufacturability, performance, and reliability. The traditional planar, we have a repeatable because it's gate planar, as I mentioned in the trench devices, any misaligning makes a lower yield, as you can see here. But we also have high yield in the traditional planar and low cost because we need lower masks or lower steps in the fabrication compared to the trench. In the performance, obviously, trench devices have lower R-on-SP or lower RDS-on at the same active area. As I mentioned, we have higher channel mobility, and also the cell pitches are smaller, and also faster switching because of the lower CGD here. But the performance here, another performance comparison is the temperature coefficient. Normally, we have a lower temperature coefficient for the planar compared to the trench. And finally, in the reliability, as I mentioned and explained in the trench, we have a higher electric field at the gate oxide, and it causes lower reliability, lower short circuit capability, and failures due to non-uniform gate oxide. Now, by combining the advantages of both these technologies, we can have all the good things in trench-assisted planar technology regarding manufacturability, performance, and reliability. We have all them in one design. As I mentioned, one thing in this technology is having a unique technology for very high reliability results. Here is the result, or it's better to say this table shows the reliability for this technology based on the AEC, but these devices are not only passing the AEC, but also they are beyond the industry norms. So we named it AEC plus qualification. All the green numbers here are the numbers that are higher than the standard that needs to provide the silicon carbide devices. For example, for power cycling, we have more than 30K cycles. Dynamic reverse bias, or DRB, 1,000 hours to 3,000 hours, which is a huge time for the DRB. The DGS, more than 1.5 trillion cycles. HTRB, 1,000 hours, and so on. But if you look at the HTRB here, we have 200 degrees C instead of 175. HTGB and HTRB, 200 degrees C at 1,000 hours. And finally, we have a VDS of 100%, 100% instead of 80% at 1,000 hours, and there is no failure. This slide compares the VTH stability with these different technologies: trench-assisted planar, commercial planar silicon carbide MOSFETs, and trench devices. Obviously, in trench-assisted planar devices, we can see a lower shift of the threshold voltage compared to both other technologies. Here's the resistance or temperature coefficients from room temperature to 175 degrees C. We compare 2.3 kilovolt Navitas devices with the two other vendors, 2 kilovolts and 2.3 kilovolts. And obviously, we can see lower temperature coefficients compared to the both actually vendors, 20% compared to one of them, and 17% lower than the other component. And this is one thing that I mentioned. We have better current spreading at our design, and also the drift layer has been optimized regarding the doping concentration and thickness for this lower temperature coefficient. Here is a comparison of our technology, trench-assisted planar technology, with trenches and planar regarding the UIS, or unclamped inductive switching. In order to have a fair comparison, we normalize this actually energy, this energy to the active, based on their active areas. So we have a fair comparison. A and B are the trench devices, and this one is Navitas semiconductor or manufacturer with trench-assisted planar technology. D and E are planar technologies. Obviously, we can see we have a better capability of UIS compared to the trench devices, because both trench-assisted planar and the planar are the planar gates. And as I mentioned, we have a better shielding of the gate oxide. And this is the reason that we have better energy energy compared to the trench. Also, here is the IDS peak or the peak of the current, and again we normalize it based on their active area. Both of them are at 175 degrees C, so they are at high temperatures. And again, we have a better capability, UIS capability regarding the high current compared to the trench devices. Here is the TDDB results. We are considering the lifetime for our gate oxide by applying a high voltage, 8 megavolt per centimeter, 9 megavolt per centimeter, and so on, in order to find out the lifetime at the recommended operations. If you look at this picture, it shows that the failure time for 18 volt, which is the recommended operation, is more than 1 million years. And the failure time at 175 degrees C at the maximum operation, which is the 22.5 volt, is more than 1400 years, which is obviously higher than the lifetime that we need. Now let's look at the ultra high voltage silicon carbide technology, 3.3 kilovolt and 2.3 kilovolts. Here's the latest results that we achieved with 2.3 kilovolts, again, utilizing trench-assisted planar silicon carbide MOSFETs. Here's the RDS on versus temperature from -55 to 200 degrees C with a VGS of 18 volt. And obviously, by increasing the temperature, the RDS on is increased. And at room temperature, we have an RDS on around 23 to 24 milliohm. Here's the breakdown voltage at 500 microamps. At room temperature, the breakdown voltage is around 3 kilovolts for 2.3 kilovolt class MOSFETs, and we have a stable breakdown voltage. And as you know, the breakdown voltage is increased in silicon carbide devices from low temperature to high temperature a little bit, and we can see this trend here from -55 to 200 degrees C. So at 200 degrees C, for example, the breakdown voltage is around 3.1 kilovolts at 500 microamps. But in the 3.3 kilovolt MOSFETs, we use 2 channel lengths in order to have a good R&D. We have a longer channel and also shorter channel. Again, here is the RDS on versus temperature from -55 to 175 degrees C. Obviously, we have a lower RDS on in shorter channel because the RNSP in shorter channel is lower than a longer channel. But if you look at here in longer channel, you can see that the RDS on is roughly constant from -55 to 0 degrees C. And the reason is there is an offset between the longer channel resistivity and the drift layer resistivity. But in the shorter channel, we can see the RDS on is increased from low temperature to high temperature. And at 25 degrees C, we can provide RDS on around 45 milliohm. Here's the breakdown voltage for both shorter channel and longer channel at 500 microamps from -55 to high temperature 175 degrees C. Again, we have a little bit lower breakdown voltage in shorter channel compared to the longer channel. So obviously, if you compare the shorter channel, longer channel regarding the forward characteristics and breakdown or reverse characteristics, we can see that we have a lower RDS on and a little bit lower breakdown voltage in shorter channel. However, even for shorter channel, the breakdown voltage at room temperature, which is at 25 degrees C, is around 4.15 kilovolt for 3.3 kilovolt class. So it is more than enough for these products. And again, the breakdown voltage for both of them are increased from low temperature to high temperature for both longer and channel. Here's the UIS robustness for 2.3 kilovolts. The VDS reached to around 3.5 kilovolts before the failure, and we have a higher, the peak current before the failure around 52 amps. The avalanche energy is 4.31 joule. And now if you look at the UIS capabilities for both shorter channel and longer channel in 3.3 kilovolts, you can see the same capability for both of them with avalanche energy of 4.4 actually joule, 4.44 and 4.23, so it's negligible. We have the same capabilities with the same peak current and avalanche voltage. For the voltage, it reached to around 4.5 kilovolts, and the current reached to around 44, 45 amps. So obviously we can say that our devices, or these 2.3 kilovolt devices and 3.3 kilovolt devices utilizing this technology, are robust. Now let's talk about the epoxy resin potting power module technologies that we developed in Navitas. First of all, let's look at the traditional modules. In these traditional modules, we have the DBC, which is the copper ceramic substrate, copper DBC, and then we have the silicon carbide chip, which is bonded with the wires, and we have die attached over the DBC. And then after that, we are pouring the silicon gel in order to have this module. In Navitas, we developed a technology, and in this technology, actually, we replaced the silicon gel with epoxy resin. So as a good comparison, or apple-to-apple comparison, or P2P, we compared our technology with this technology and just actually replaced the silicon gel to epoxy resin in order to have a fair comparison. So all parts are the same, and the only difference is just the epoxy resin. And here is the reliability results for both. Temperature cycling from minus 55 degrees C to 150 degrees C. Navitas with epoxy resin, more than 1,000 cycles, it passes. But if you look at the silicon gel, less than 100 cycles, it fails. Thermal shock test from minus 40 degrees C to 125 degrees C. Again, passes more than 1,000 cycles and fails less than 100 cycles. And the temperature humidity bias, H3TRB, high voltage H3TRB, this module passed in the module level, 80% VDS, 1,000 hours, and also die level, 80%, 1,000 hours. But another technology for silicon gel, the module was failed. We have only the die level only for 1,000 hours, 80% VDS. How this epoxy resin helps us to improve the reliability? First of all, reduces variation of plastic strain of bond wires. The epoxy reduces the strain between the DBC here and the wound wires. The second one is reduces expansion stress due to higher thermal conductivity. This epoxy resin has about 10 times higher thermal conductivity over gel. So obviously we have a quickly spreading heat. Then we have limits extension of and bending of overall structure. Epoxy limits extension and bending of DBC. And finally, this epoxy resin can prevent of moisture penetration into our module, but silicon gel can absorb water, moisture, and contaminants. As I mentioned, we designed this module in order to have 10x better thermal shock reliability. Now let's compare the epoxy resin with silicon gel in this shock reliability test. Here is the DBC picture at time 0. After 100 cycles, as you can see, there is nothing in the epoxy resin. But if you look at the silicon gel, you can see some degradation in the utilizing the silicon gel on the DBC. Now, after 500 cycles, we can see conchoidal fractures in the silicon gel, but a little bit, just a little bit at this part and this part with the epoxy resin. And finally, after 1,000 cycles, you can see a lot of conchoidal fractures with the silicon gel. But again, a few parts here affected with the epoxy resin. So we can say that up to 15% thermal resistance increase for epoxy resin, but in silicon gel, we have 33% to 80% increase of thermal conductivity for the silicon gel. And all epoxy resin potted modules passed isolation test, but all silicon gel modules failed isolation tests. And here is a comparison of power cycling lifetime between these two type of modules with epoxy resin and silicon gel. And as you can see, we have more than 65% compared to one vendor and 70%, more than 7% compared to another vendor, higher power cycling. And it shows that over 65% longer lifetime compared to the pair of silicon gel, that is, as I mentioned. So with that, 3.3 kilovolt and 2.3 kilovolt silicon carbide or SiCPAC G plus modules that we are developing features newer technology that will enable significant longer lifetime. This diagram shows the number of the cycles versus the difference of TVJ or the junction of the difference of the temperature of the case. Now let's look at the future technologies. As I mentioned in the previous slides, the grid tie applications operating from 13.8 kilovolt to 34.5 kilovolt needs a higher voltage power semiconductors, because with higher voltage silicon carbide devices, 2.3 kilovolts and above, we have higher efficiency, a smaller footprint, and increased reliability. However, when we are increasing the voltage, it means that we need a thicker drift layer. One challenge in the silicon carbide is the basal plane dislocations, or BPDs. When we have a high current in the PN junctions here in the body diode, we may receive to a conductivity modulations where we have the both electron and holes, and these electron and holes can recombine in the BPDs, forming the stacking faults. And these stacking faults are growing in a 4-degree angle, because normally we are using a 4-degree off-axis silicon carbide these days. So suppose that we have a very thick layer of drift layer, and these stacking faults are growing in 4-degree angle. By increasing the thickness, we have more area that is affected with these stacking faults, and finally we have the bipolar degradation. One way in order to overcome this issue is instead of using the body diode here in this PN junction or pin diode here, we can integrate the Schottky diodes or JBS or MPS inside the MOSFET. If you look at here, we have the MOSFET cell here on the left-hand side, and also another cell of the MOSFET on the right-hand side. We are utilizing our technology, trench-assisted planar technology, so you can obviously see this multi steps of P+ in order to protect the gate oxide of this MOSFET cells. But at the middle of these two cells, we are integrating the Schottky diodes here. So as you know, the Schottky diodes have a lower VF, and it means that the body diode will not be triggered, and we have the current in the Schottky diode, and we are preventing of the bipolar degradation. Here is one example of high voltages that we use this technology, 6.5 kilovolt silicon carbide MOSFETs with integrated MPS diodes. The blue line is discrete MOSFETs, and the red line is the diode MOSFET at room temperature and high temperature. As you can see, in the diode MOSFETs have a little bit lower current compared to discrete diodes, because discrete MOSFETs, because we are actually sacrificing one part of the active area for these diodes. And here is a comparison of RNSP for both diode MOSFETs and discrete MOSFETs. Obviously, you can see that the discrete MOSFETs have a lower RNSP compared to diode MOSFETs. As we mentioned, we are sacrificing one part of the active area, and it means that we are increasing the RNSP. But the difference is only 5%, not more. So RNSP of the discrete MOSFET is 37, and diode MOSFET is only 39 milliohm centimeter square, only 0.2 milliohm centimeter square. These discrete diodes MOSFETs show RDS(on) of 300 milliohm with a VTH of 3 volts. Here is the breakdown voltage of 6.5 kilovolt MOSFET with integrated MPS diodes. Again, the blue line shows discrete MOSFETs, and the red line shows a diode integrated MOSFET. If you look at here, we have a breakdown voltage around 7 kilovolts for this class of 6.5 kilovolts. But if you look at very carefully here, you can see we have a little bit higher leakage current in the red one, which is the diode MOSFET. Now here is the IDSS in microamp level for both discrete MOSFETs and diode MOSFETs. And if you look at or compare these two, we have only a little or a small difference between the discrete MOSFET and diode MOSFETs. 0.07 microamps for the MOSFETs and 0.09 microamps for diode MOSFETs. So we have very small difference in the leakage current, even if we are using these Schottky diodes. If you know, the Schottky diodes normally have leakage current compared to the PIN diodes, for example. But we have seen a very small difference here. Here's a short circuit with stand time and UIS capability for these devices, 6.5 kilovolts. The VDS for short circuit with stand time is 3.6 kilovolt with a VGS of 20 volt and minus 5 volts at room temperature. If you look at the data, we can see we have a high short circuit with stand time of 6 microseconds. And finally, for the UIS capability, here is the drain voltage. We can see we have a high peak between 7 to 9 kilovolts before the failure, and the peak current reached to around 7 amps before the failure with avalanche energy of 2.62 joules. So we have a high capability of the UIS. Let's summarize my talk. The exponential growth of AI workloads is transforming the data center landscape. The traditional silicon-based power electronics and 54-volt architectures are no longer sufficient to meet the multi-megawatt requirements of next-generation AI factories. As I mentioned, we need higher voltages. Otherwise, if we increase just the current, we have a lot of power loss. The transition to an 800-volt DC architecture direct from grid to GPU makes a fundamental inflection point, enabling megawatt rack level power delivery. Then we have the GeneSiC MOSFETs for AC grid to 800-volt DC conversion, rugged and reliable. We can support different parts of the data centers. Navitas delivers robust, efficient, and scalable solutions purpose-built for AI factories. I explained about the trend-assisted planar technology, which offers highly reliable, high performance, and robust silicon carbon MOSFET suitable for high and ultra-high voltage applications. And also, I covered the use of epoxy resin putting in power module technology, which improves the reliability, as I explained in the previous slides and compared with the silicon gel. And once more time, Navitas can support the data center grid to GPU from 100 to 200 volt gallium nitride, 650 volt bidirectional gallium nitride, and the silicon carbide. We have a wide range from 650 volt up to 10 kilovolt and even higher, which can support different parts of the data centers: SSD, UPS, BBU, air conditioning, and server power. By this QR code, you can actually find more information about Navitas and our products. You can connect with Navitas with LinkedIn, Facebook, YouTube, X, and WeChat. And thank you very much for your attention.
Thank you, Arash. Thank you for the presentation. We do have some questions that has come in. So the first question is, are there any of the 800-volt data centers with solid-state transformers in operation yet?
It is the future technology. So honestly, I don't know if we have any prototype of 800-volt AI architecture now or not, but it will be for sure for future technology.
Okay, thank you. The next question. What kind of termination used for 6.5 kV MOSFET?
We are using this actually. I can't say everything about the technology here, but normally we are using, or it's better to say roughly the same trench technology that we are using for 2.3 and 3.3 kilovolts.
Okay, thank you. The next question. What makes trench-assisted device best for data centers?
First of all, as I mentioned, we have a trench-assisted planar technology, which is more reliable and robust. We have a high UIS capability. We have high short-circuit instant time. Our reliability is more than the standard, and also we have a lower temperature coefficient compared to the other technologies. So it makes these devices very unique for these applications.
Okay. Thank you. And the next question, does it still make sense to use trench-assisted planar technology for 6500 volt and higher voltage nodes?
Would you repeat that question again?
Does it still make sense to use trench-assisted planar technology for 6500 volt and higher voltage nodes?
Yes, absolutely. We have a lot of advantages by using this technology. As I mentioned, we have a better protection under the gate oxide, which makes a more reliable device. And also, it comes from the planar. So we are going to stay in the planar. Also, we have a lower temperature coefficient in the planar. We have better UIS capability in planar. So all of this makes us to use the gate planar technology. Regarding the other thing, and if we compare the trench-assisted planar technology with the traditional planar technology, as I explained, with this technology, we are able to reduce or shrink the cell pitch more than the traditional planar technology, and it results a lower RNSP, which is a big and huge advantage.
Okay. Okay, next question. As the solid-state pulsed power gaining traction, do you have any roadmap to look into high-peak current power devices?
We are working on the roadmaps, but unfortunately, I can't actually reveal the roadmaps here. Sorry.
Okay. Thank you. Okay, the next question is regarding the recording that was going to be available after this. So yes, we will be posting the recording on our Power America membership portal, which will be available to our members. Okay, any other questions? Please type in in the Q&A box.
And sorry again for the fire test alarm. It was not actually on our hand. It was actually done by the fire system outside of our company. So sorry again for that.
I forgot to reset the clocks on Saturday night.
Yeah. It's okay. Okay, looks like we don't have any other Q&A, but audience will have the QR code and your email. If they have more questions, they can reach out to you.
Absolutely.
Okay.
And I'll be so happy to answer any question that comes from my side. This is my email address, and you can actually send any question that you have.
Okay. Actually, Araj, we have one more final question. Does
Absolutely.
the US military use Navitas products?
We have different customers from different aspect areas.
Okay. Okay, thank you everyone for attending today's webinar. And thank you, Araj, once again for taking your time and to, accept the invitation to run the technical webinar for Power America.
Absolutely. It was my pleasure. Thank you very much for your kindness and also inviting me for this webinar. Thank you very much.
Okay.
Don't forget to join Power America for those who are not members. Thank you, Mr. Rush.
Okay.
Thank you, everybody. Have a good rest of your day. Thanks again.
Bye-bye.
Thanks, Victor. Thank you very much. Bye.